Hello students, in this problem we're going to find the area of an ellipse. Now you may recall that the area of an ellipse is pi AB. We're going to derive that result where A is going to be the major axis and B is going to be the coordinate for the minor axis. Now we're going to do so using double integrals, and we're going to transform from a circle, which we can find easily enough the area of, to this ellipse. So we're going to use a change of variables to derive that formula pi AB. So the transformation we're going to come up with, if you notice, if we let u be x over a and v be y over b, then we get the equation for this unit circle is just u squared plus v squared, right? Because if u is x over a, then that's u squared plus v is y over b, that's v squared, and that's equal to 1. So here we had the ellipse, and here we have the circle. So we have the mapping from the circle to an ellipse. So now once we have that mapping, we're about to change variables for our integral. So now that I'm getting ready to do that, I'm just simply going to solve for x. So now I have x as a function of u and y as a function of v. So I have my transformation. T of uv is au and bv. So this here is the x coordinate. This here is the y coordinate. Now I'm going to convert, these are my area integrals. So remember, the area integral, the area of the region D, is just simply the integral with a 1 in here. So you can imagine there's a 1 for the integrand. And I'm going to write it this way: dA in the xy coordinate system, and then I'll have dA in the uv coordinate system. And then of course I have to do my change of coordinates, so I have to put the Jacobian in the integrand, and I'll use c for the circle. So what we're going to do now is compute the Jacobian and then compute this integral. We compute the Jacobian. That's simply, remember, that's going to be dx dy dx dy, so you can think of the dx dy in the numerator. And then we do the first variable first, so it's dx du dy du, and then the second variable next, which would be v. So in the second row we have dx dv dy dv. So the derivative of x with respect to u is just simply the derivative of this coordinate, and that's just a. The derivative of y with respect to u, that's the derivative of bv with respect to u, but there's no u term, so this is a constant, so we get a 0. And then similarly, dx dv would be 0, and dy dv would be b. So when we take this determinant, we get a multiplied by b. So now we have that this integral in the uv coordinate system is simply a times b, and then we just have the area element. So that will now give us the area of D. To do this integral, we're going to convert to polar coordinates. So we're going to do yet another transformation. So we're going to transform from a rectangle in the r theta coordinate system to the circle in the uv coordinate system. And recall that when you do this change to polar coordinates, the transformation is a phi r theta, which is r cosine theta, r sine theta. Then you take the Jacobian, the derivative of u with respect to r, which is simply be cosine theta. The derivative of v with respect to r would be sine theta. The derivative of u with respect to theta will be minus r sine theta, and the derivative of v with respect to theta will be r cosine theta. And then when you take this determinant, you get r cosine squared plus r sine squared. You factor out the r, and you're simply left with r, because cosine squared plus sine squared is equal to 1. So that r is the Jacobian. So that allows us to convert this integral in the uv coordinate system to one in a polar coordinate system, and the area element now becomes r dr d theta. The AB is a constant. We're going to factor that out of the integral. We integrate the r, we get 1/2 r squared. It's going from 0 to 1 because that's a unit circle. And if I just stick the 1 in there and subtract the 0 using the fundamental theorem of calculus, I'm left with the 1/2. I factor the 1/2 out, and I have AB over 2. Then I integrate 0 to 2 pi of d theta, and I'm just left with a theta. now I use the fundamental theorem of calculus. I have 2 pi minus 0, so I have 2 pi times ab over 2. The 2's cancel, and I'm left with pi ab, which is what we thought the area of D was going to be, and that is the area of the ellipse. And that is how you find the area of an ellipse using double integrals and change of variables. All right, good luck.